Hi everyone, I am Megha. Today we have to study about the topic Subring. First of all, we can understand the definition of the commutative ring. Let R be a set on which two binary operations are defined called addition and multiplication. Then R is called a commutative ring with respect to these operations of the following properties hold. The properties are R is an abelian group under addition, multiplication is associative and commutative. R has a multiplicative identity element. Next, the distributive laws hold. Now we can study about the subring. The definition is let R be a commutative ring. A subset S of R is called a subring of R if it is a commutative ring under the addition and multiplication of R and has the same identity element as R. Proposition let R be a commutative ring and let S be a subset of R, then S is a subring of R if and only if S is closed under addition and multiplication. If A element of S, then negative minus A is element of S. S contains the identity of R. Proof of the proposition is let R be a commutative ring and S be a subset of R. First, suppose that S is a subring of R. Then by definition, S is a commutative ring under the addition and multiplication of R and has the same identity element as R. Since S is a commutative ring under the addition and multiplication of R, the closure axioms must certainly hold in S and so S is closed under addition and multiplication. Also, S is an abelian group under addition of R and so A element of S implies minus A element of S. There is negativity exists. Finally, the definition of a subring demands that the subring must have the same multiplicative identity and therefore the identity of R must belong to S. Hence, S is a subring of R. Hence, conclude the proof. Then we can go through some examples of subring. First one, we know that the sets of numbers set Q, R and C are all commutative rings. Also set D is a subset of Q, Q is a subset of R and C is a subset of R. And 1 is the identity element of all these rings. Hence each one is a subring of the next larger set. The next example is consider the commutative ring set 6. Let S equal to set of 0, 2, 4. Then S is closed under addition and multiplication and contain the additive inverse of each element in S. Since the subset S also has an identity element, namely 4, this shows that S can be considered to be a commutative ring under the operations on set 6, but we do not consider it to be a subring since its identity element is not the same as the one in set 6. Now we can study units of a commutative ring. Let R be a commutative ring. An element A element of R is said to be invertible if there exists an element B element of R such that AB equal to 1. In this case, the element A is called a unit of R and the element B is called a multiplicative inverse of A, usually denoted by A inverse. From the properties of a group, it follows that if A element of R is invertible, then the multiplicative inverse of A is unique. Since 0 into B equal to 0 for all B element of R, it is impossible for 0 to be invertible. Furthermore, if A element of R and AB equal to 0 for some non-zero B element of R, then A cannot be a unit since multiplying both sides of the equation by the inverse of A would show that B equal to 0. When thinking of the units of a commutative ring, Here are some good examples to keep in mind. The only units of set, the set of all integers is 1 and minus 1. The set of units of set n, the set of all congruence classes modulo n are the equivalence classes A for which a n equal to 1. Hence for all integers n, set n cross is the set of all unit of set n. For any commutative ring R, R cross is denote the set of all units of R. Proposition. Let R be a commutative ring, then the set R of units of R is an abelian group under the multiplication of R. Proof. Choose any AB element of R, then A and B are units of R and hence they are invertible. Therefore, there exists A inverse B inverse element of R such that A into A inverse equal to 1 equal to A inverse into A and B into B inverse equal to 1. We can also written as which 1 equal to B inverse B, where 1 is the identity element of R. Then since multiplication is associative in R, we get AB into B inverse A inverse equal to 1 and B inverse A inverse into AB equal to 1. Hence AB is invertible and so AB element of R. Hence R is closed with respect to multiplication. The identity element of 1 is always invertible and hence 1 also element of R. For any A element of R, A inverse element of R and A inverse all inverse equal to A. Hence A inverse is invertible and so A inverse element of R. Since R is a subset of R and multiplication is both associative and commutative in R, it follows that multiplication is associative and commutative. Thus, R satisfies all group axioms under multiplication and multiplication is commutative in R. Hence, the set R of unit of R is an abelian group under the multiplication of R. Next topic is divisors of 0. Here said to be the commutative ring of all integers under the operations usual addition and multiplication. Here 0 is the additive identity for any mn element of Z, mn equal to 0, if and only if m equal to 0 or n equal to 0. But in the commutative ring Zn, the set of all congruence classes modulo n. Congruence class 3 into congruence class 2 equal to 6, which is equal to also congruence class 0, even though congruence class 3 not equal to 0 and 2 not equal to 0. These observations lead us to the following definition. If A and B are two non-zero elements of a commutative ring R such that AB equal to 0, then A and B are divisors of 0 or 0 divisors. Last proposition is the cancellation laws for multiplication hold in a commutative ring R if and only if R has no divisors of 0. Let R be a ring with no divisors of 0. Then for any ABC element of R with A not equal to 0, AB equal to AC, which implies AB plus minus of AC, which is equal to AC plus minus of AC, which implies AB minus AC 0. Then common a നെ outside എടുത്താൽ a into b minus c equal to 0, b minus c equal to 0, which implies b equal to c. Similarly, we can show that ba equal to ca, which implies b equal to c also. Thus, if R is a ring with no divisors of 0, then the cancellation laws hold in R. Conversely, suppose that cancellation laws for multiplication hold in R. Then for any ABC element of R, AB equal to AC and A not equal to 0, which implies B equal to C by the left cancellation law. B equal to CA and A not equal to 0, which implies B equal to C by the right cancellation law. For any AB element of R, AB equal to 0 and A not equal to 0, AB equal to A into 0 and A not equal to 0, which implies B equal to 0. AB equal to 0 and B not equal to 0 ആണെങ്കിൽ which implies A equal to 0. Thus AB equal to 0, A equal to 0 or B equal to 0. Hence the commutative ring has no divisors of 0. Now we can discuss a problem related to this topic. Prove that in the commutative ring Z, the divisors of 0 are precisely those non-zero elements that are not relatively prime to n. The solution is, first we choose any congruence class M element of a Zn where m not equal to 0. Let the greatest common divisor of m n equal to d ആണെങ്കിൽ first let m be not relatively prime to n, then d is not equal to 1. Since d is the GCD of m and n, d divides both m and n, and hence both m divides d and n divides d are positive integer. Congruence class m into congruence class n by d equal to m into n by d, which is equal to 0. Hence m not equal to 0 and n by d not equal to 0. Therefore in this case m is a divisor of 0. Now let m be relatively prime to n, then d equal to 1, and for any s element of Z.